Back in 2008, the smartphone landscape looked very different. The first commercial Android phone, the T-Mobile G1, featured a bulky slide-out physical keyboard and an interface that was extremely basic by today's standards. Compare that hardware-heavy brick to the sleek, entirely digital environment of Android 15. The operating system has evolved into a hyper-connected environment, handling millions of calculations a second. This pie chart shows the projected global smartphone market share for 2025. You can see Android holding a massive 72.5% of the market, leaving Apple's iOS with roughly 27%. Apple achieves its slice of the pie through strict control. They build the iPhone hardware, and they write the iOS software that runs on it. The two are inextricably linked, designed specifically for one another. Android operates in complete contrast. It is a single piece of software that must function across tens of thousands of different devices, from a folding flagship tablet to a $50 prepaid phone, with completely different screens and cameras. Scaling a single unified operating system across literally thousands of unique hardware configurations creates an immense logistical complexity. The puzzle is how Android remains a unified platform while the underlying parts are in a constant state of flux. This diagram illustrates the structural answer, a rigid, hierarchical 5-layer architecture. To understand how Android stabilizes thousands of hardware variations, we have to strip this stack down to the bare metal and build it back up. At the absolute bottom lies the foundation of the entire system, the Linux kernel. This schematic of Layer 1 highlights why Google chose the Linux kernel. It acts as the engine room, handling the grueling, invisible tasks. The icons show it manages physical memory allocation and uses its driver model to route data to raw hardware. But this creates a massive bottleneck. A specific proprietary hardware component, like a custom Sony camera lens, needs exact electrical instructions to work. The generic software running up above has no idea how to speak to that specific circuit. Layer 2, the hardware abstraction layer, or HAL, steps in to solve that problem, acting as a universal translator. Instead of learning every camera's language, software simply sends a generic snap command. HAL translates this into precise electrical signals for that exact lens. Because of this translation layer, manufacturers like Samsung, Xiaomi, or Motorola can swap out physical components at will. They just update the HAL file, while the core Android software above it remains unchanged. This slide outlines Layer 3, the execution engine. The Android runtime, or ART, optimizes application code into native instructions for mobile processors to save battery. Meanwhile, native libraries like OpenGL and WebKit handle the heavy lifting for 3D graphics and web rendering. Layer 4, the Java API framework, is the control center for developers. It provides a pre-built toolbox so they don't code basic functions from scratch. To manage how an app opens, they call the activity manager. To pull an icon, they ask the resource manager. Finally, we reach the absolute top of the hierarchy, Layer 5, the system apps. This is the only layer the end user ever actually interacts with. It houses the factory defaults, like your dialer and email, along with every single third-party application you download from the store. When a user effortlessly swipes across a glossy app interface in Layer 5, they are completely insulated from the complex mathematical translations happening down in the metal kernel of Layer 1. The architecture absorbs all the friction. This table shows the direct trade-off of this structure. On the left are the benefits, boundless flexibility and an open ecosystem. But on the right, weaknesses emerge. Thousands of hardware variations cause software fragmentation, and extreme customization drains battery life. Beyond battery drain, there is a much more critical vulnerability. Because Android is an open system that allows users to sideload apps directly from the web rather than a strict app store, it creates an exposed target for malware. This slide details the architecture's digital immune system. The first line of defense is absolute isolation, or the sandbox. The rule is strict. Every application is locked inside its own virtual environment, completely blocked from accessing data inside other apps without explicit user permission. To back up that physical isolation, Android employs an active defense layer called Google Play Protect. This always-on machine learning engine scans up to 100 billion apps every single day. It functions as an invisible, intelligent shield, autonomously hunting for digital anomalies and malicious code in the background, without the user ever noticing. Android's market position is the result of this layered engineering. By separating the user from the hardware and the apps from each other, the system provides open-source flexibility while maintaining the stability to power the world's mobile devices.